All right. So opposed to the next individual assignment, it'll be kind of related to some of the stuff that we were doing in Excel with like the normal distribution, some of the stuff we ended last class and we'll start today with, which is the exponential and the log normal. If you want to change data sets from whatever you use for your first individual assignment, let me know as soon as possible, or if you think you need additional variables. You should only need like 2 variables in your data set, but they have to be, at least one has to be continuous. Actually, both of them would need to be continuous, but I think you could technically use a discrete variable, and as long as you had the functions right, it should work okay. So we'll kind of pick up on what we left off with last class and just kind of review that. Just kind of. So the first thing I want to do before we kind of jump back into the log normal is, oh, I scrolled down too far, is look at an example that I had set up. I don't know, I was interested in this at some point, but I forget what season it was now. I feel like it was maybe 2016 or 17. The Cubs, a big Cubs fan, had a high number of wins, but ended up, I think, 3rd in their division. And so I got kind of interested in this idea of what number of wins would get you first place in your division. And so I pulled a bunch of old data, right? And for each year, I calculated for that division what number of wins would have got you 3rd place, what number of wins would have got you 1st, and which would have got you 2nd, right? So I kind of graphed out that number of wins that would get you 1st place, and sure enough, I mean, a little bit off of a normal distribution here, but if I break this up a little bit differently, kind of looks like a pretty close to a normal distribution. So if I treat this as though it's normally distributed, I can actually start to find the probability that if I had 100 wins, what would be the probability that if I had 100 wins or more, that I actually get 1st place that year, right? So I set this up in Excel, just to kind of show you could really do this with any variable that you want, right? As long as it looks like it's normally distributed, right? I've got kind of my 1st place number of wins that would give me 1st place variable here. So I calculate the mean of that, right? Just using that average function. Let me blow this up a little bit here. All right, I can calculate my variance pretty easily. Just use that sample variance. I didn't have every year, I guess, prior to 62. Okay. I then found my standard deviation by just taking the square root of that variance. So I now have a mean and I now have a standard deviation. I can start to answer questions like, if I won 97 games or a small number of games, what's the probability that I would get 1st place that year? Right? Get rid of this here. So all I do is choose that cutoff value I'm interested in. I could take my mean, my standard deviation. We said we always use kind of (1) for that cumulative. And I can find that probably be 66, 67%. If I said, okay, what's the probability that if I win 97 or more games, right, that I would win that year? About 33%, right? And I think that year, so there's a 33% chance if they won 97 games or more, they would have got 1st place. And that year, they ended up getting 3rd, right? So you can start to play around with some interesting things like that. Really any variable that you're interested in. And this was just something that I was interested in, did for like 15, 20 minutes. Grabbed a bunch of old data, saw that it's normally distributed. You can start to get probabilities like that pretty quickly using that norm.dist function, right? I don't have to go through, calculate the z-scores. Excel will do that for me. So this is very similar to the idea, or the example I showed you with like temperature and rainfall. But just something that, you know, to show you can really do this with any variable that's normally distributed, okay? So I think what I played around with, right, yeah, 66%. What's the probability that if you get 97 games or more, you get 3rd place? So I set that one up on the same thing. But obviously the number of wins that would get you 3rd place is a lot smaller of a mean. So I did the exact same thing. I used this norm.s.dist, or sorry, that norm.dist function. I don't know why I forgot the dot there. Use that value of 97, mean, standard deviation, (1) to make it cumulative. I get that probability was what, 0.02%, right? And you could play around. I could change the 97 to whatever value I'm interested in, maybe, I don't know, 88. Oh, what did I do there? 88. Why is it giving me a negative value? Oh, because I was playing around with kind of subtracting something here. So we could actually do 1 minus that, so about a 5% chance. But you could answer a bunch of different probability questions. What's the probability if I win between this many games and this many games, right? And then we would have a little bit more work to do for that fourth step, which we said was transformation, right? If I just want the probability of being less than something, when I go to the table, I've got my answer. If I want the probability of being between two values, right? And I think here what I did was 95, and originally I had this set as 97 games. So if I win between 97 games and 95 games, what's the probability? Well, that would be just take the larger probability, subtract the smaller one. Now I'm just left with what's in between, and that's where I was getting that kind of 0.02%. So that fourth step is really specific to whatever probability you're looking for, whatever the actual example is. Okay, so that's just a little bit of review. Also do a little bit of review of this log normal, right? So the idea that we kind of started out here was, I have this variable y. That's what I see in the data, okay? I know that it's log normally distributed. So if it's log normally distributed, that was when we said that whatever variable y I have is equal to e to the power of x. Now x, we know, was a normal distribution, right? But in order to get the mean of x and the standard deviation, or the variance of x, I had to use those two equations to convert the mean and the variance I see for y so that I can compute what those are, right? And the reason why we said y was log normally distributed, because if I rearrange things to solve for y here, this is what I get, right? So let's go here in Excel at that Indiana weather data set. Oh, actually, this is the wrong file. This is from my other class. You guys are lucky. I don't make them do that. Just you guys. So where's that Indiana? There we go. All right. So EXP and log normal. So this is where I had this variable of income. If I knew it was log normally distributed, well, the variable I actually see, or that y variable, is here in my data set. Okay. So I can find the mean just using that average function. I find the variance just using my variance function. Here we'll treat this as a sample. To convert those into my mean, so you think about this here, I said expected value of x. Another way of thinking about this is the mean, oops, put a space in there, or the expected value of x. All right. I think someone asked me last class, I'll replace the file after today with what we've done in class, the old complete one. I added we did a couple different things here, so you'll have everything that we looked at. So I've got my variance, I've got my mean. Basically at this point, I just have to use Excel as a calculator. So all I'm doing here is entering in this function. Now the mean that I'm using and the variance that I'm using, actually kind of denoted it here, I think a little bit better, is the mean and the variance I see for that y variable that's in my data set, right? So I'm just putting into Excel this function, right? When I do that, to do the natural log, I just use ln, and then whatever's within there, it takes the natural log of. Notice my mean squared divided by the square root of my mean squared plus my variance. So remember, when you see sigma squared, that's your variance. So if I calculate the variance, I don't have to square it again. Now, if I had found the standard deviation and plug that in, well, yeah, then I have to square that, right? But if I found the variance, that is sigma squared. So when I'm looking here, I just have the variance of that original variable. I can see y. And then solving for the variance of x, I can use this equation. So we go back. That's what I did right here. Now the only difference is I took the square root so that I got the standard deviation instead of the variance. So if I have the equation for the variance, standard deviation is just take the square root of that. Now that I have this mean and this standard deviation for this underlying variable x, well, I know x is normally distributed. So now I can use that mean and that variance I calculated to find the probability of different cutoff values for y. When I'm looking up those cutoff values for y, I don't put in just the value of y, I have to put in whatever the natural log of y is. Because it's the natural log of y that is equal to x, which is normally distributed. Right? So when I'm looking at what I did there in Excel, once I get to this point, let's say the cutoff I'm interested in is 20,000. Well, now it's just using that norm.dist function. The cutoff I want is the natural log of 20,000. I select that mean that I had to calculate for x. and that standard deviation I had to calculate for x. Now, it's kind of a pain that we have to kind of keep going back from variance to standard deviation, but the way that this function works in Excel is you have to tell it the standard deviation. If I instead had found the variance, then here I would have to have like the square root of whatever cell my variance was in. And then once again, always count one. Always use this idea of cumulative, the area to the left, okay? So the other way that we could do this, we said there's this log norm function, and it's the exact same thing. The only difference is you don't have to take the natural log of whatever cutoff value you're interested in. It will take the natural log for you, okay? And we had the example that we worked through in class, and I kind of set up in Excel. I'm not going to really have you do too much of this by hand. I think in the Connect, you can do some of this by hand, but if you want to use Excel for the Connect problem as well to solve and come up with your answers, that's fine. Right? So that's just kind of a review of this log norm. Are there any questions on that? Because I know we kind of ended and kind of ran out a little bit of time last class. So I wanted to kind of review that and go over how you would actually do this with a value or with a variable in Excel. Okay with this? Yeah? Okay. Good. All right. All right, let me double check. I was gonna say, let me make sure I'm recording this. I keep having these like leave the oven on moments when we do these sometimes that I didn't hit record. So another trick we could do, and I'm not gonna kind of push you guys this far, but it's a very similar idea. I just want to kind of go over it. So if I know that X is normally distributed, this mean of 9, variance of 81, and that Y is equal to the square root of X, right? Well, then what I actually know is if I rearrange this, is that X would be equal to Y squared, right? And it's a similar idea as what we were doing up here. It's just that now X is equal to not the natural log of Y, but Y squared. So I could do the exact same thing. If I know that X is kind of this normal distribution, then I could convert kind of my values, my cutoff values I'm interested in by squaring them. Now that I know that this is X is equal to Y squared, it's the same sort of process because I know X is normally distributed. I could find what the mean and the variance of X would be, right? Whereas if I know, if I can find the mean and variance of Y, I can convert those because it's going from squared to something squared, right? It's a lot easier than when I was using this natural log, right? So you could do the same sort of idea. I'm not going to kind of push any of this. The only one we're really going to focus on is this log normal. I'm not going to waste too much time on the other one because I'm not going to give you any problems on that or expect you to kind of know that. But we could start to think about other transformations as well, not just this log normal. Okay. All right. And this kind of details the steps of how we would do this in Excel. I kind of already walked through there, but this is a nice kind of summary slide. Okay. I'll end with that because I love that meme. So we're going to take a kind of a step back, and we want to get to a point where we start talking about the distribution of sample means, right? So everything we've talked about with all these continuous random variables, these are all assuming, right, if we go back, that we know the population mean and variance, or even if we go further back, right, I need to know the population mean and the population variance. Well, a lot of the times we don't have population data, right? So if we only have sample data, what do we know is going to be true about those sample means that we see? Now, I can't quite get there yet. I want to talk a little bit about how we make sure that if I'm only seeing a sample mean, how do I ensure that sample is reflective of my population, right? So we usually have finite or infinite populations, just for the sake of kind of going through this a little bit quicker. We're only going to be dealing with things that have finite populations, right? The population of the US, right? It's a large number, but it is finite. Right? So we're going to be dealing with finite populations. It's not feasible to get this population data, maybe with a census, but we said those are expensive, hard to do every year. And so I'm stuck using this sample to make inferences about the population. All right? Now, some notation we've already talked about, just to set this up, is our population is size capital N. The size of our sample is going to be lowercase n. So our sample is going to be a smaller amount of observations than the entire population. Okay? So we can randomly select or randomly choose observations or elements to put into our sample, right? Now, if we're randomly doing this, we can do it two ways, with and without replacement. So the idea of with replacement is if I have a hat, let's say for this class I want to randomly sample 5 of you. Put all your names in a hat, draw one out. Maybe I want to look at your height. Write your height down, put your name back in the hat. Draw another name, write that person's height down. Put the name back in the hat. That's doing it with replacement. Without replacement is if once I draw a name and record that height, I throw that one in the trash. I can't draw that from the hat again. So which one do you think is probably more useful to us to use, or probably a better one to use? With or without replacement? What could happen if I'm using with replacement? Yeah, I could select the same person twice, right? Repetition of my observations. Well, when I have a sample, I want each observation to kind of carry the same weight. Well, if somebody's in there twice and everyone else is only in there once, that's not going to work, right? In fact, if I'm taking small samples and I had maybe a relatively small population, I could maybe draw the same person 3 or 4 times, even if I'm only selecting a random sample of 5. Well, that's a problem, right? So most of the time, it's better to do this without replacement. There are cases where it's not, but for the most part, we're always going to be thinking about examples where we have our sampling process has been done with out replacement, right? So we can only see each individual like one time. Okay. All right. Some other things that we need to make sure, although this is almost every example we'll look at, this is going to be true. So each element or observation is going to have to come from the population you're interested in, right? If I'm interested in the average income in the US and I can only take a sample, I don't want to be sampling someone from Canada, right? They have to be from the population I'm interested in. They need to be independent. So sometimes where we could see this be violated, if I'm doing something with survey data, it's hard to get people to respond. I call someone, they actually respond and give me whatever information about the variables I'm interested in for themselves. I then say, well, is there anyone else in the household that I could survey? Well, especially majority of people living in households not college age might be like families, right? Well, now I know that families have similar characteristics, so I'm kind of going to be an overrepresentation of those. So I don't want them to be dependent, right? They need to be truly independent. But even given that, we still have some issues, right? Let's say I'm interested in the average height in the US. I randomly sample, 20 people, and it happens to be that 15 of them are female and 5 are male, right? Well, right away, I know that average height of that sample isn't going to be what the true population, or I know it's going to be off of what the true population mean is, because I knew for the population, my gender breakdown is pretty much 50-50, right? Maybe a little bit off in one direction, but definitely not 75%, right? 15 out of 20. And so I want to ensure that my sample, yes, it's random, but I want to make sure on this one characteristic that it's reflective or it matches the population, right? Reflective of the, so what I would do is I'd break it down into these kind of 2 non-overlapping groups. And for the sake of this example, if you don't want to think about it as kind of making gender binary, think about it as, people with, we could do this by, if I'm doing a height, what's another good one I could do? Maybe I'm looking at weight, and I could break this down by age groups, right? Non-overlapping age groups, okay? So I would say choose, I'll use a gender example just because I think it's easy. I know there's some problems with it, but bear with me for a second. So let's say I want 100 people in my sample, right? I know that I want to have a gender breakdown that matches my population. I'll randomly select 50 males, I'll randomly select 50 females, and then I'll put them together to get my full sample of 100. Now I know that my gender composition of my sample looks the same as my population. I could do the same thing by, and this is all I'm saying here, so we break them down into each stratum, and then randomly sample from each one of these stratum, and then throw those together to make my full sample. We could do this by age groups, right, to make sure that the age distribution of my sample matches the population. We could do income, make sure that my income distribution of my sample might look similar to my population. And that's because I know that income, age, gender might be related to a lot of other variables I might want to be looking at, right? So for the income one, think about if I'm interested in where maybe the political leanings of the country at the time. I know that income is pretty correlated or has some somewhat related to, income is somewhat related to political party identification. And so I want to make sure that for my sample, my income distribution in that sample kind of looks pretty similar to what my population does. So I might say sample 20 people to make between 20 and 40,000. maybe only 15 who make between 40 and 60, right? Or whatever numbers would give me a similar distribution that matches up to the population, or at least what I think the population looks like, okay? Like I said, I always use gender as the easiest idea because we know that it's about a 50-50 kind of split, okay? Cluster random sampling is almost the same exact idea. I'm never going to expect you to like identify, was this cluster or was this stratified random sampling, but you break it down into subpopulations. So it's not that, you know, you're breaking it down based off one characteristic, but you're looking at little small scale versions of the entire population. So maybe if I'm interested in something like, I don't know, like some type of lung health measure of people who live in big cities, my population is like every city over 1 million maybe. I could then look and sample, say, 10 people from every single city that's over 1 million and then throw them all together in my final sample. Now I make sure that each one of these kind of subpopulations, right, each one of these little cities is represented. But I wasn't breaking this down based off of a characteristic I think was related to maybe the variable I was trying to record, okay? So basically it's a very, very similar idea, and we can start to do things like this that help make sure our sample looks similar to our population. Right? I have a political poll example here. You know, if I was interested in what's the outcome of the next election, I just want to ask people, you know, are you going to vote for Trump or not? Or are you going to vote for Biden or not? Well, if I only ended up with people from the South in my random sample, I just happened to randomly select people from the South. Well, I know that the South, the political breakdown there looks very different than the country as a whole. So I might break the country down into regions, Southwest, Northeast, and then randomly sample a number of people from each one of those regions and then throw them all together. Right? And maybe even randomly sample a number of people from those regions that match whatever their population kind of percentages of the entire country. Right? Okay, so with this idea, if we wanted to get our sample to kind of match our population, what could go wrong, right? So there's this quick example, and I think it gets at two biases that are really important, and I think it's a pretty good way of looking at it. So the 1936 election, Alf Landon lost to FDR, right? Great name. Sad he's not one of our presidents. So in 1936, right before the election, like right about now, the Literary Digest poll sent out like 10 million survey cards, right? 2.5 million people responded. I don't know if you've talked in other classes about surveys or done a survey. A 25% response rate is pretty damn good. It's hard to get people to mail things back to you, right? So they have, and it's a ton of observations, right? It's not the population, but 2.5 million is a big sample. Well, the responses predicted that Landon was going to win in a landslide. Like 57% of the popular vote, big electoral college, win. But we obviously know that Roosevelt won, but in fact, he won in an even greater landslide than the prediction that the Digest poll had for Alf Landon, right? So they got it way, way wrong, right? So what went wrong? This is all stupid stuff, right? Math errors, they use population instead of sample variance. Those are just me kind of being, what could have went wrong in this calculation? Well, what if they'd only sent these mail cards or these surveys to Republicans? Well, if I only send them to Republicans, I'm for sure going to get a skewed result for my sample, right? About which way the election is going to go. Even if I sent 5 million to Republicans, 5 million to Democrats, if only 2.5 million Republicans responded and 0 Democrats, well, that's a problem too, right? So we can kind of break these things down, and we have a more generalized name that isn't specific to this example. So those things are the selection and the non-response bias. So a selection bias would have been, did I systematically over-select a certain group to be in my sample? That would be the idea if I only sent these surveys to Republicans. The non-response bias is there's a systematic difference between groups in their response rates. You can think about it that way. So even if I would have sent 5 million to Republicans, 5 million to Democrats, if the Republicans' response rate was much higher to this survey than the Democrats, then I'm going to end up with a sample that has way more Republicans kind of than I know what the breakdown of the population looks like. Because at any one point in time, we've got about a 50-50 breakdown between Republicans and Democrats, right? That's why we continuously go back and forth between our presidents, right, from the different political groups, okay? So this is a selection non-response bias. How could this maybe have existed in this survey that was given? Well, what the digest, this literary digest did was they used telephone books and cross-referenced it with car registrations to get their name of people they would send these surveys to. Okay? In 1936, who owned cars and telephones? Really rich people, right? And we know that, I mean, well, I shouldn't say we know. If we look at the data that's out there, we know that income is correlated with political party affiliation, and it tends to be that higher incomes tend to vote a little bit more Republican or kind of right-leaning, right? So right away, we know that we're going to have a selection issue. The people in our sample are more likely to be from higher income brackets, which we know are more likely to vote Republican, right? So there's kind of our selection issue. And if we look at, so there's this paper that went back and tried to interview people or find the people from these surveys and ask them who they actually voted for, right? So kind of looking at this after the fact. And what they found was for people who owned a car and a telephone, right? 53-ish%, right, of people actually did vote for Landon. So yeah, if I only surveyed people who owned cars and telephones, that sample would have actually been right, right? The problem is not everybody owns cars and telephones. So if we looked at, even if we only looked at car registrations, 60% of people who only owned a car and no telephone voted for Roosevelt. 62% of people who only owned a telephone ended up voting for Roosevelt. And people who owned neither, well, 73% of them ended up voting. Well, these people here weren't sent mailers, right? And so that's why our prediction was so far off what was actually ended up being the result. Right? So that's interesting evidence of a selection bias. What about this non-response bias, right? Well, I had 75% of people didn't respond. What percent of the people that did were Republican and kind of what percent were Democrats? So they went back again and said, okay, if you owned a car and telephone, did you send this, did you receive the survey and did you send it back, right? Well, for people who owned a car and telephone, oh, I don't want that yet. The people who ended up voting for Roosevelt, only 17% sent the survey back. For people who voted for Landon, only 35% sent it back. So we had almost like more than twice as high of a response rate for whatever reason from people that were going to vote for Landon. So like, it's not a digest fault necessarily, but there was this huge non-response bias as well, right? The people who ended up voting for Roosevelt or kind of Democrats just did not respond to this survey for whatever reason. And I'll put a couple files up on Canvas of a paper, this actual paper. I forget their exact explanation. It has something to do with income being related to this. And so if you're from lower income groups, you might be less likely to respond to surveys, or, you know, the literary digest was viewed in a certain political leaning. And so if I'm on the opposite end, I might be less likely to send my survey back there as well. And you kind of see, though, it didn't matter. Even if they wouldn't have used cars and telephones to get these names, if you only own a car, only own a telephone, or you own neither, right, the response rates were always higher for people that ended up voting for Landon. So I don't know, kind of, you know, like I said, I forget their exact kind of reasonings behind this, but for whatever reason, they were more likely to send that survey back. So we had a selection and a non-response bias built into this, and that's why they got it so wrong. And I think this political example is a pretty good one for kind of getting at what those two biases look like. So what else can go wrong, right? So first, people can lie to you when you're collecting data, right? Either maliciously or non-maliciously. They might be lying to you on purpose. They might be lying to you because they forget about whatever question you're asking, right? If I ask you, how much money did you spend on X, Y, and Z, I might not remember the exact amount. I'll give you an amount. I'll probably like round it, right? So I might tell you it was $100. Maybe it actually was 92, right? So that's kind of non-malicious lying. People might just misunderstand the question. So there's a lot of, I think, research in psychology that looks at this, like just the framing of questions. You can elicit different responses. I saw Fox do this thing once where they put two questions up, and the result, like it was something about whether or not people thought Trump was doing a good job in office. And just the way in which they phrased the question, there was like a 10% difference in kind of, you know, the results of the two questions. So just the way in which the question's asked can elicit different responses. So we, you know, worry about that as well. So we'll work through a couple examples here, and we'll think about all these biases that could exist, right? So let's say, usually I'm able to do this with clickers and we can kind of look at the data, but let's say I asked everybody in this room, or even in the Zoom call, what you would rate your health from 1 to 4 today, right? Well, what are some biases that could exist in this? Well, first of all, if I think about the selection bias, if I'm asking you guys about your health and I'm interested about the health of the US, why would I have a selection bias? I'm over-selecting young people, right? Hopefully, young people, I mean, on average, young people are much healthier than 80-year-olds, right? And so I have a selection bias that I over-selected from a young age group, and I know that's not going to match up to the country as a whole. Right? What about my non-response bias here? Well, you probably could think about this might work in two directions. If I'm very healthy, right, maybe I'm more likely to respond to this question to let you know how healthy I am. If I feel very unhealthy, maybe I'm less likely to respond to this because I don't want you to know how unhealthy I feel. And so both of those things will end up with a final sample where you have healthier individuals, right? Because you're missing some of those non-healthy people who weren't as likely to respond. Okay? Some kind of lying, well, people on average think that they're not as healthy as they are. Like it's interesting, even with a group of college students, when I look at the responses to this, the average is not 1, it's almost always like a lot of 2s. But you guys are probably a lot healthier than you think. Even if you don't feel too well, relative to the entire population, you're not doing too bad, right? I could have just misunderstood the question, right? I always end up with a couple people when I'm able to do this with clickers where they respond with a 4. And, oh, I thought that was the highest, right? I just read the question quick. I was thinking a higher number meant better. And so you could have kind of, that's like a non-malicious lie. They didn't mean to give you false data. They accidentally misunderstood the question. And I kind of have all these things lined up. Another one I want to point out here, and hopefully the variables we're dealing with are continuous. But if you force this to be discrete, I'm almost forcing some of you to lie to me. Because if you feel like a 1.5, you have to respond with a 1 or a 2. So I'm not really getting your accurate feeling if I make it discrete. So we want to try not to do that, right? Not to make the responses discrete. I was asked this one, so how many alcoholic drinks do you have on average? Well, this one we've got a pretty easy, I think, to think about these biases. So if I have a selection bias here, what might be one group of individuals who maybe are less likely to respond to this question? Well, if I'm drinking like a, people less than 21. So that would be, let's be careful though, right? So people less than 21 would be less likely to respond. So that would be kind of my non-response bias. If I think about my selection bias, who am I choosing to fill out this survey? College students. What do you think is probably true about college students' drinking behavior relative to the country as a whole? Quite a bit higher, right? So I've got my selection bias. You got your non-response bias from the people who aren't 21 who might not want to say, well, I don't want Professor Lance to see that I'm drinking more than 12 drinks a week, and I'm not even 21, right? So, we've got some selection biases there as well. You might have some malicious lying, people just telling me 0 if they're not 21. So even if they respond, giving me a 0 response, right, giving me this 0. Could have people, there's always the one guy at the party who wants to tell you can drink a lot, and so maybe you have some over-exaggeration in that, and so we've got malicious, non-malicious lying that we could think about probably going on here as well. So all this being said, right, we can't completely eliminate all these biases. We can do the best that we can, but we want to think about when we're dealing with sample data, how might this sample and the way it was collected not be reflective of the population as a whole, okay? All right, I think we already mentioned those. I'll go through this because I think it's kind of interesting. I'll put this paper up there as well on Canvas. They had this paper that kind of talked about the last election, and they looked at a bunch of exit polling and different things, because every political poll in the last election got it wrong, right? I shouldn't say everyone. Most of them had a prediction that Clinton was going to kind of win the election. Obviously, that's not what happened, so what went wrong, right? I don't know exactly how every political poll is done, but there could have been some selection bias in terms of if they were only calling people from certain areas, large versus like urban versus rural, less educated versus kind of more educated, right? We might tend to be kind of have lists of people that are don't represent, or that not every group is represented in the list of people that we're calling or sending surveys to. But the real one this paper focuses on is kind of these malicious liars. And it's the same idea with a big non-response bias that existed. When I'm asking someone who they're going to vote for, they ended up figuring out with exit polling is a lot of people who were going to vote for Trump just either didn't respond to polls when they were being surveyed, or they said they were undecided, right? And this idea that they were shy Trumpers, where they knew they were going to vote for Trump, they didn't want to make it known, right? They didn't want to actually say that to someone when they were on these call lists, right? So this, I think, one of their kind of conclusions or suggestions at the end of this article was, maybe we try to make political polling less personal and like try to do this like completely anonymous online, as opposed to like hearing someone's voice. If there's any type of social pressure with admitting to voting for a certain candidate, well, then you're going to end up with people who are maliciously lying to you or just not responding, right? And then, of course, you could have the unintended lying here, which is that people just switch their mind from when the polls were taken to when the election actually occurred, right? And I imagine all these, I don't think, this non-response and this malicious, these shy Trumpers, I don't necessarily see that being an issue that was solved. So I always look at political polls right now and take it with a grain of salt to think about, are they actually capturing the accurate representation of the population as a whole right now? And like I said, to me, it would seem like we want to do something where we have a lot more anonymity so that we can maybe reduce some of these biases. Right? But that's kind of a nice application of when we're talking about how we think about these biases existing. All right. So I'm going to start off. So we got about 15 minutes. All right, that's good. So we're thinking about now we have these samples. Let's say we've done things correctly. We've eliminated these biases, biases. I don't know why that sounds the same way. So I have this sample mean that I can now calculate, right? I've gotten together this sample. I can calculate my sample mean. Well, if I only take, say, a sample of 10 people, right? It's very likely, if I'm thinking about maybe average income, right? If I end up randomly selecting Jeff Bezos in that sample mean is going to be way off of what the population mean is. Now, if I get a sample of, say, 1 million people and Jeff Bezos ends up being in there, well, he's not going to influence the mean near as much in that larger group, right? So I know that these sample means, how far away they are from the population mean, or how likely it is that I see them be different than the population mean, will depend on the sample size I take, okay? So what ends up being true is, if I were to be able to take, let's even say we wanted a sample size of 100 people. If I took a random sample of 100 people, calculated the average income, wrote it down. Randomly sampled another 100 people, calculated their sample mean, wrote it down. I continue to do this, right? Maybe I do it 1,000 times. I've now got I could have a data set of 1,000 sample means. Okay? If I have 1,000 sample means, I could create a histogram pretty easily out of that, and the sample means would have their own distribution, okay? So if we were to take samples of different sizes, what ends up being true is those sample means have different distributions, right? Because the idea was, let's say I took samples of size 1, and I'm looking at income. Well, if I take samples of size 1 and I end up selecting Jeff Bezos, I'm going to end up with some ridiculous number, right? But if I take samples of size 10, even if he's in my sample, that sample mean is going to be much, much, much lower, right? So even if we think about this as kind of the range of possible values we could see, kind of varies depending on the sample size that we take. Right? So if we're able to look at these samples, right, of the same size, like my idea that I had 1,000 samples of size 100, what's going to be true about that distribution? What's that distribution going to look like? Okay? What ends up being true is that from a sample of size n, right, lowercase n, if I had a population mean and a population variance, and let's say I was able to view the population data as well, the mean of my sample means will always be the population mean, right? So if I was thinking about those 1,000 samples of size 100, the mean of all those 1,000 sample means would end up being whatever the true population mean was, okay? And I have kind of a data experiment where I'll prove this to you, but for now, just kind of believe me, right? But yeah, the mean of those sample means, so the mean of my sample means will always be whatever the original population mean is, okay? The variance of my sample means always ends up being whatever the original variance was of the data I was sampling from, divided by my sample size. And this is kind of related to the idea of as I take samples of larger sizes, I'm kind of reducing the range of possible values I could see for the sample mean, right? If I take samples of size 1, we'll use human height. I can see someone who's 7'2". If I take samples of size 100, the probability I see a sample mean of 7'2" and 100 people, if I randomly select them, is almost 0, right? And so that variance of my sample means is directly related to the sample size I take. And as I take a higher sample, what happens to the variance for those sample means? So if that sample size goes up, the variance of my sample means, dividing by a larger number, variance of my sample means goes down. So if I get really, really large samples, I can like guarantee that there's a very low variance in my sample means. Or if I have a low variance, what I'm saying is it's not very unlikely I see values far from the mean. Well, if the mean of my sample means is the population mean, then for really, really large sample sizes, I'm guaranteeing that my sample mean is going to be very close to that population mean. Right? And that kind of directly comes from this idea that it's inversely related with my sample size. That variance of my sample means inversely related to my sample size. Okay? And we already, hopefully we know the notation here. Here's our kind of population variance. Here's our sample size. Okay, I kind of already mentioned this. I guess the other thing is, obviously, if there's more variation in the original data we sample from, well, then the variance that we could see for our sample means is also going to be higher. Right? I already mentioned this idea of how the sample size is related. I think this goes without saying, right? If the variance for the original data gets higher, the variance I will see for my sample means also gets higher. Another thing here. So in some of the formulas that we'll start looking at, here, let me go to the board real quick. If I'm thinking about, so here's the variance of my sample means, right? If I want the standard deviation, I just take the square root of that, right? So this represents the standard deviation of my sample means. But another way of writing this that will sometimes be more useful in different formulas that we'll look at is if I take the square root of something that's squared, that's just the same thing, but I still have to take the square root of the denominator. So this also represents the standard deviation of my sample means. It's just a different way of writing it mathematically, okay? So we'll kind of use it in both forms, right? And that's all that I'm trying to get at here. We can see this in either two formats. All right, so, and this will always kind of be true. So let's say I have all this birth weight data, and I have every birth in Indiana in 2004, right? So I can view the population mean for Indiana births, and I can view the population variance. So let's say I have this in a huge data set, and I calculate those values. I then randomly sample 36 babies, right? And I calculate their sample mean birth weight, sorry. If I were to say take 1 million different samples of size 36, what would be true about the distribution of those sample means? Well, the mean of those sample means should be whatever the original population mean was. And then the standard deviation of those sample means, we go back, well, that would just be take the original variance, divide by the sample size, and take the square root, right? So I take that original variance, divide it by the sample size of 36, I get what? 10,000 there, take the square root, should be 100, right? So I think I used the other format here, which was first calculating the standard deviation, which was 600, then dividing by the square root of n. So we could do that either way, right? But once I do that, I'll end up with a standard deviation of 100, okay? So like I said, for now, just trust me that these are true. Next class, we'll walk through, I have some kind of visuals that we can do, and I have this kind of data experiment to prove to you that those are going to be true. All right. Here's another example. If we took samples of size 100, right? What's going to be true about the mean of those sample means and the standard deviation of those sample means? Well, the mean of those sample means should just be the population mean still. Taking samples of larger sizes doesn't change what the mean of those sample means will be. What it does change is the variation or the standard deviation I'll see on those sample means. So if I take larger sample sizes, where's that quit? There he is. If I take a larger sample size, I know that the variance of my sample means should go down, right? Because if the denominator gets larger, then the whole fraction gets smaller. So when I think about the first example, if I took samples of size 36, there my standard deviation was 100. So if I take samples of size 100, I know my new standard deviation has to be less than 100, right? So when I look at these possible answers, well, the only one that makes sense is that the standard deviation would be 60, and then of course the mean of my sample means is always just whatever the original population mean was from the data I sampled from, right? Or C there, okay? And you can calculate it, right? You could use these equations, plug in our values, so I'll use this one. So it would be what? The square root of 360,000 divided by 100, which if you put that in your calculator, you should get that 60, okay? Any questions on any of this? Kind of just setting us up today for what we're really going to dive into it on in Friday's class. But at least want to introduce this idea of the distribution of sample means today. Okay. And then I'll leave you guys with this. We'll end a little bit early. This is like one of my favorite memes. I guess we could change it. But if hotness was a normal distribution, you'd be 3 standard deviations above the mean. I always say you could change this so you'd be a z-score of 3. And then like if they don't understand what that means, you know that they're dumb and you should just walk away. All right, well, I'll leave it at that. We'll pick up next class, talk more about the distribution of these sample means, and then start to talk about things like confidence intervals, okay?